see you. Welcome back. Got a full house again today, love it. Got the creepy screen here, which means I've remembered to record. So I gave back all of your homeworks. For the most part, I think everything was fine. If you have any questions about whatever I asked you to do differently, or if you need to do something, let me know. I also tried to weigh in on whether or not you needed to subset what you were looking at to do analyses with your own data. If you're not sure what that's going to imply, let me know, but we're still a few weeks out from thinking about that. And no homework due this week, no quiz this week, but I did move actually your second quiz to be due on Wednesday of next week instead of Monday. That way I make sure we hit all the stuff that I want to be on it. So just that one update. I think that was what I wanted to say about that. So any thoughts, questions before we dive back into the story? Nope, we're good? We're ready? All right. So let me hit a few review slides before we get back into the example. So we are doing confirmatory factor modeling, or confirmatory factor analysis, as it were. And we're going to be worried about item things and factor things, where factor is the latent trait, latent construct, latent variable, true score that we're interested in. So just to remind you, each item in these models is going to be characterized by three things: an intercept, a loading, and a residual variance. Just like in regression, intercept is the expected item response when all the predictors are 0, which is, in this case, when the factor is 0. The slope is the loading here. That's the change in the item response for a 1-unit change in the factor. And E is the idea that there's variance left over. So E is the specific residual for each specific subject and item. Its estimated model parameter is its variance across people. So the model doesn't do a perfect job of predicting Y, so we have E left over. So that same idea gets depicted graphically here. This is slide 10. So this is an example of what a two-factor model would look like for 6 items, 3 on each factor, where the measurement model is item things. So the aforementioned intercepts connected by this vector of 1 stupid triangle thing here. Loadings, which are the labeled paths from the factor to the item. So note the direction. That's another way to convince people you don't know what you're doing, is to get the arrows backwards. I've seen that before. I want to make sure the arrows go down into the boxes, because the trait causes the answers to the questions. And then we have the error variances indicated by these circles here, meaning they are estimated things, just like the variance of the trait is estimated. And then on the structural side, that's factor things. Those are your factor means, factor variances, factor covariances. So we have to find some way of figuring out all of those different things at the same time, and to do that we have to nail them down, and that's known as identification. So that's where we were talking about last time. So do you remember how the model predicts, let me go back to the picture here, the relationship between 2 items on the same factor? Do you remember? Follow the paths. 2 items on the same factor, their covariance, for instance, Y1 and Y2. You start at Y1, you go up the path to the factor, you pick up the factor, and you come back down the path for Y2. So it's the loading times the variance of the factor times the loading of the other item. Over here, it would be the same thing between any 2 items on this same factor. And to get from one item on one factor to one item on another, again, start from Y1. Let's go up the loading, across the covariance, and down the other loading. And it works out mathematically that the factor variances don't apply. So it's just each of the loadings multiplied together times the covariance. So the whole point of this exercise is to explain the patterns of covariation among these responses, not their actual variation. So I was thinking about this, and how do I explain the difference in this? And an idea came to me, so I'm going to draw for a bit here. So let's say I'm drawing my little factor model here. I'm going to have 4 items, and I'm going to have a circle that's something like satisfaction with life. There's a classic scale that measures this, that it has at least 4 items on it. You may have heard of this before. So I'm drawing my arrows from the circle down to each of the boxes. And these would be the responses to each of my items, 1, 2, 3, 4. And this model is trying to say, okay, so why did you answer question 1 the way you did, and question 2 the way you did, and question 3? Well, because I'm satisfied with life. But what makes you satisfied with life? I don't know, right? That's the big picture question of the world, right? What makes for a good life and happiness and meaning of life? I believe the meaning of life is 42. Am I correct on that? I read a book once where they told me that, and I've maintained that. But no, I have a hypothesis about what causes satisfaction with life is the number of times you look at Facebook every day. That's my hypothesis. And I believe that it actually negatively impacts your satisfaction with life when you see everyone else having way more fun than you did, right? All the stage photo ops of people with their perfect children and perfect places, and you just feel like a loser by comparison. So this is my hypothesis. So you can kind of think of this as a mediation sort of model. The goal of putting in a predictor like number of times you looked at Facebook is to explain why some people are more satisfied than others. That's a truly like explain, capture, variance, R square would apply kind of thing. And the idea then is that any response to these 1 items has to go through this latent factor. So the reason that I answered number 1 the way I did is because I have this level of satisfaction with my life. Now, what causes that is up for grabs, but I have a hypothesis that it's due to at least one of these things. So number of times that I look at Facebook indirectly predicts my answer to number 1, but only so much as it predicts satisfaction, which predicts my answer to number 1. So the goal of the trait is to explain the covariance. It's not to explain why there is variance in the way that we typically think about explanation. The top part of this would be the structural model. From Facebook predictor to satisfaction with life, that's structural. That's trying to say why some people have a higher factor score than others. The bottom part, the measurement model, is simply trying to get an estimate of what someone's satisfaction with life is. And for that to be a valid estimate, the way that we demonstrate empirically that it is plausible that these items measure one thing is that the pattern of covariance that exists in the data is adequately mapped by the pattern of covariance that's predicted by the model, where the model is loading times variance times loading. How far off you are from what the data says to what the model says, that's model fit. I can give you a more realistic example of this from my life if you'd like, but let me pause for a second here and ask, does this make sense? Does this help at all? Maybe? Maybe. Yes, so the idea that number of times you look at Facebook can predict satisfaction with life, which in turn predicts your answer to number 1. Like that's only a plausible thing to the extent that you can say that number 1 is measuring this construct. So it's the idea that our evidence that there is one thing in common across these 4 items, that is empirically demonstrated by comparing what these items have in common in the data, their covariance matrix, with what the model says their commonality should look like, which is loading times variance times loading. The extent to which those match is model fit and is support for the fact that there is one thing in common under these items, and that thing is whatever you've named it here. So whether or not I've named this appropriately is a validity argument, and that would be shown by its association with other things. But whether it's just one thing, period, is reliability, and that's what these models are designed to test. Unidimensionality and reliability, I should say, under that same umbrella. One thing and measured well, one thing.
I have a question, but it might be too far away, so you can skip it. So the idea that certain items would be related to each other through a particular factor sounds like in longitudinal when certain time points are more related to each other because they happen from a particular person.
Yes.
How do those ideas overlap?
They are the same idea.
Okay.
A latent variable is a random effect.
Okay.
They are the U's. A factor score is like a random intercept, but weighted differentially as a function of the items. Yes. So the factor variance and covariance matrix is the analog to the G matrix, and the residuals among the items would be the analog to R. And that's why the very end of example 4 has this same model in proc mixed, so that folks who've had multi-level or longitudinal can try to put these things together as they really are the same thing. Other questions? So I can give you an example of when this goes wrong, such as when I'm talking to my 3-and-a-half-year-old. He is ostensibly potty trained, but every now and again I show up to pick him up at school and there's 3 bags of clothes waiting for me in the cubby, which can only mean something very bad when it happened during the day. And so his indicators would be something like, I have a latent variable of had an accident, and I know that because there's wet underwear, there's wet pants, there's wet shoes. Yes, shoes. I've learned that any kind of shoe is machine washable if you want it to be. And a negatively reverse-coded item of wet t-shirt, meaning that if your t-shirt is dry and everything else is wet, those are my indicators that he has had an accident. And I try to ask him, buddy, why'd you have an accident? Because my pee-pee went all over. Like, nope, that's the definition of an accident. What I'm asking is what happened, right? Were you distracted? Were you asleep? Were you trying to make your teacher angry? All of these are plausible explanations. But I had an accident because my pants are wet is not a plausible explanation. So I thought that might help, but that's an example from my world, right? He didn't explain why he had an accident. He just told me that he had an accident, and these are all indicators that he had an accident. I once got sent a website, I'll have to see if I can track it down, that described cancer as a latent variable in the same way. There's all these symptoms and signs and blood work that you do, and it's this latent condition that, based on the indicators, they think you have. It kind of works the same way. But what causes cancer? Not the fact that your white blood cells are high, right? So this is describing the phenomenon. It's describing the commonality across the items. Why people have different levels of the trait, we still don't know, and that's not the point yet. We get to find that out once we know that we have adequately represented our items with enough traits to make sure that we know what we're measuring. All right, how are we doing? Okay. So I want to go back to M+ in example 4, because I think that putting numbers on this is going to help get these ideas in a way that just talking about them abstractly is less useful for. So, I know I wanted to show you. I mentioned something at the end of class that I realized I had already put on your webpage for the class. At the top of the webpage for the class, there is a link to Lisa's M+ guide from pilesofvariance.com. If you go to that, you will need this for your second assignment, by the way, which is not yet available. This describes the rules of M+ syntax, as well as how to get data into it. So I have what the data have to have in terms of their characteristics, as well as example code for how to export your data from various programs. So for instance, in SPSS, you would use save translate. In SAS, it's proc export. And in Stata, it is export as well. So one of your first tasks when you start to use M+ is to build a data set to use with it. And I want you to give that a try. And here are some resources by which you can do it. And I'm sure you can get it through the point-and-click menus as well. But I wanted to make sure that you had code to go into your programs as well. So this is an extra resource beyond just the specific examples that we do in class that's more M+ generic. Ours are going to be more latent variable specific. Okay, so this was a true story. 6 items that ostensibly measure one thing, forgiveness in situations. 3 of them are written negatively, 3 of them are written positively. I showed you their correlation matrix, And I look at correlations because those are easy to understand in terms of what their values mean. What we're actually going to be working with in terms of the model, though, is covariance. So here's the formula by which you get covariance. It's the correlation times the standard deviation of each of the two indicators. So once you have either the variance or you have either the correlation or the covariance, you can work back and forth so long as you've got the variance as well. So this right here, this observed covariance matrix, this is essentially the answer key. In multi-level terms, this would be an unstructured covariance matrix. Everything gets to be what it wants. It is the data. This is the answer. Our job is to create a model that predicts that as close as possible. And the model that I hypothesize is responsible for all of these covariances is that these are 6 items measuring one thing. Each of them measures it differentially well, and that's why the covariances and the correlations are not all the same. Question?
You're in example 4, right?
Yep, I am. First page. Excuse me. Yep.
Oh, I was just looking for the circle.
Yep. Here we go. Yes. Yeah, so the idea is that the only reason that there are these correlations between these items is because they're all measuring one thing. The reason that they are different in correlation is because each of them measures it differentially well. That's the hypothesis that we're putting on this data. And we will get back a predicted matrix, and literally the difference between that and this one that the data gave us, that's what we're going to pay attention to. But probably get to that next week. So I put these plots out here to make a point. There's a whole lot of literature looking at how many categories is enough for an ordinal scale to declare it continuous and normal. And the prevailing wisdom is somewhere around maybe 5 or 7 is what most people would say. But that's not actually enough information. You have to know how your people used the scale. So in this case, these are, I would say, not quite normal. They clearly have a ceiling effect where most people picked the highest category. They're skewed. So the extent to which we can fit a linear model predicting each of these responses from a factor is up for debate, because the linear model is going to predict that some people would have answered 8 or 9 or 10, even though they can't. It's unlikely to be a problem on the lower end because of the way the data is set up, but if you have a trait where most people answer on the lower end, the opposite pattern would happen. The factor model would predict negative responses that are implausible. So it's not just the number of categories, but how they're distributed. And we will see how to make predictions to try and indicate whether or not the predictions are reasonable by a linear model. So that will be coming up shortly. So in M+, things in after an exclamation point are comments. Their commands will turn blue when you're running the program and everything else is black. So things to note, the data file. As I said last time, this is text data. It's either a tab delimited file or a comma separated values file or a fixed format file. I prefer CSV most of the time, but you can make any one of those. If you do a fixed format, you have to tell it how it's organized, and so that one takes more work. If your data set is stored in the same physical directory as your syntax, you don't have to say where it goes. Like when it runs the syntax, it's going to look in the same folder for the data. If your data are not stored there, you need to put the path to it instead. Because these are text files and they tend to be really small, I tend to just make copies and stick them everywhere so that I don't have to write the path names down, but that's up to you. It wants to know then the names of every variable in your data set in order. And I will tell you, I would say in troubleshooting people's models for this class in the past, at least 50% of the time when people come to me and say, my model fits terribly, I don't know what to do, it's because they missed a variable and it never read their data in right. It is super easy to do that. Like in SPSS, if you filter certain cases out, it automatically makes a new filter variable at the end for you, and if you export and forget that that's there, then everything is going to be off by one column when it reads it. So I cannot stress this enough. Make sure that you check and double check and triple check that you have the right variables in the right order, otherwise everything you do is going to be wrong. And there are ways to check it built into the program, and that's one of the first things that I will have you do in your assignment as well. It will spit back descriptive statistics for your variables, the means, variances, or frequencies, and you can check those against your data to make sure that they match, that it's reading it correctly. So that's the names. The next one here is use variables, and this is just the stuff that's going in your model. If you forget this line, it tries to model everything at the same time, even your ID variable. So here, I am writing out the names of my variables with R's after the ones that are reverse coded because it will help us keep track of what happens. As I said last time, if you wanted to be to type less, you can do something like this, sit1 to sit6, and it will expand all of those. If you give it a common stem, you don't have to write them all out. You do have to indicate your missing values, and I am, as I said before, superstitious. I always fill them in because I've had bad luck when I didn't, using blanks or dots as the missing data codes. Yeah, question?
So right here you're saying fill in blank or dots with this number, or what's happening here? Are you just telling it that it's missing, or you're not replacing anything here? Just
nope.
Telling it?
When I built the data set, in the last step before I exported it, I replaced all of the missings with that number. And I'm happy to share code for that if you need some. But yeah, I can't claim that that's entirely necessary. Like I said, that's my own superstitious behavior. I've had bad experiences otherwise. ID variable allows you, if you were to export factor scores, to have that column in there so that you can merge them back into your data, but that's not strictly necessary.
Those are the good kind of factor scores, not the bad kind of factor scores where you're not going to use...
They're the better kind.
Okay.
They're still not good, but they're better than EFA ones.
Okay. When you do instructional models, will the DV be those?
No.
Okay.
Nope. Nope. This is just if you want to make pictures or otherwise sort of describe what's going on. These are basically, it would be the U's that you're asking for that you don't normally need. Yeah, that's what this line does right here, this save data. It estimates factor scores. You don't need that. I just wanted to put it in here to show you what would happen if you did ever want to do that. For each of the analyses that we do, I will tell you what to put here. Type equals general, I think, is going to be most of what we'll do in this class, if not all. Estimator, we're only going to have two kinds. This one is MLR, which is maximum likelihood with a robust correction. We'll get into what that means, I think, in a couple slides from now. As well as some of this other stuff. The only one of these that we've talked about yet is STDYX. Can you guess what that one is? Or read from the thing in front of you. Take your pick. See, I'm shameless in getting audience participation. Standardized, fully standardized. Note, because there's STDY and STDX and STD, and this one is fully standardized with respect to both sides of the model. So that will give us our standardized loadings that will be of interest.
Can you say again what you mean by both sides of the model?
X and Y. It standardizes both the item responses to be variance of 1 and all latent variables to be variance of 1 if they weren't already. X and Y / predictors and outcomes. That's what I mean. And then everything in this example after that will go after this command called model. So that's the part that would change as a function of what the model has in it that we're specifying. Okay. With me so far? All right. So far we've talked about one of the two steps that you need to take to identify your model, which is the idea that each of these pretend variables, these circles, needs a scale. It needs a mean and a variance. So the first way that I'm going to show you is what I would recommend when you're just fitting measurement models, when you're not doing full-on structural equation modeling, which is to basically make your latent variable a z-score. So that's why I call this the fully z-scored approach. You are fixing the variable's mean to 0 and its variance to 1. That sets its scale, and the rest of the model can be found in relation to that. So here's what I have done. I have named a latent variable. I've named it sit. I could have named it factor or Lisa or whatever I feel like, so long as it's 8 characters or less. The magic command here is by. Just so you know, and when I write code, I tend to write program-specific keywords in capital letters, and I tend to write my own variables in sort of title case. M+ is not case sensitive. You don't have to follow this. I just try to do it to make it easier for you to figure out which things get swapped in and out. So by is an M+ keyword that means measured by. It means you are defining what observed variables are going to represent this latent factor here. After each of these variables, there will either be an asterisk or an @ sign. The M+ people love their special characters. They have now, by version 8.1, found something to do with every single character above your numbers, all of them. They've hit them all now. They're going to have to start using wingdings once they get to like 8.2 or something, because they're out of English characters. Yeah. Yeah, it's not case sensitive, and actually when you get your output back, it capitalizes everything. It really doesn't care. I just do that because it makes it easier to read. It's also helpful for find and replace kinds of things. Like if I had, a scale where sometimes it was going to be sit and sometimes it was going to be self, like I can find and replace capital S lowercase it and with something else, whereas if I had like in a command where there was an SIT together, where it was capital, you can do a find and replace that's case sensitive so that it skips over the ones that you don't want it to change. So I use capitalization as a way to hack those sorts of things, but it really doesn't matter. Also, the comments do not have to end in semicolons, whereas each of these individual lines do. You will sometimes see in my examples that I add semicolons everywhere just as sort of like a habit, but you don't technically need them on your comments. One last convention that is an old school convention for programming, you can only have 90 characters per physical line. You have to return after that point. So you will get an error message saying that it stopped reading at 90 characters if you disobey that command.
Is there a next line?
You can just wrap. Yep.
And then you put the semicolon at the end of the second line?
Yep. Yeah, it's not like in Stata where you have to like bar it or something. There's none of that. Yeah. So this, by the way, you can do this like this, or equivalently, if I ran out of room, I could do that. That's fine. Or another variant that is also fine. Hang on. Come back here. Hey. Is something like this. You can repeat yourself. So each of these may be useful in certain situations where other things you're typing make the line go further, but all of those are equivalent and it will be fine with them. So let me go back to where I had it. There we go. So my approach to syntax in Stata or it's not Stata, sorry, M+, and in any program is that I write out everything, even the stuff that's there by default. And that is for two reasons. Pedagogically, I want you guys to appreciate every single thing you're asking for, whether or not you know it, right, because it's doing all this stuff behind the scenes, but also because the default changes between versions. And there has been a case where the same model will give you something different in a subsequent version because they change what they do by default. So to hedge my bets, I write out everything. That means that each of these stars right here is not technically necessary. All of the loadings are estimated by default. That's what these parameters refer to, are the factor loadings, with the exception of the first one. The first one by default is fixed to 1. So if you want to override that to have a z-scored factor, you have to put a star there. And that's why down here, when I have the in reality, all you really need to write is, you still need the star here to make it not forced to 1, but you don't need the stars anywhere else.
The purpose of this was standardized, so why would you want that one to be 1?
Because we are going to standardize the factor instead. That's the other way of identifying the model. Yeah, so I'll show you how to do each way, and I'll show you how the results change as they rearrange themselves around your reference point. So these are your 6 factor loadings. That's what you're asking for. These same words inside brackets refer to intercepts or means. The difference is that an intercept is what it's called when it is an outcome being predicted by something else, whereas a mean is what it's called when it is unconditional, when it's a predictor. M+ knows, based on the context of your model, which it is. So the difference here, just let me remind you real quick, writing on the board again to encourage everyone to keep coming to class, right? I'm writing y equals beta 0 plus e. I would call this an empty regression model, meaning it has no predictors whatsoever. If I know nothing else about a person, what's my best guess for their outcome? The mean, right? So beta 0 would be the sample mean in this case. And I'm going to draw a box around the word mean. Whereas, if I write the same model, y equals beta 0 plus beta 1x plus e, now what is beta 0? Intercept. It's the predicted mean when x is 0. So beta 0 in this case is an intercept. That's the difference in interpretation. Either way, you put brackets around it, and that's what you're talking about. Either an intercept, if you're talking about a dependent variable, which is your outcome responses, or it's a mean if it's a predictor, and it's not being predicted by anything. All intercepts are estimated by default, so I don't technically need this line at all, but I put it there so that you can remember that you're actually having those as estimated parameters in the model. Likewise, the same words listed with stars again, no brackets, no sit in front of it. These are variances. And returning back to my previous example here on the board, E in the empty model, because y hasn't been predicted by anything, that's representing all the variance in y. It's literally how far off you are from the mean, which is the definition of variance. So I would call that all the variance, or variance, drawing a box around that. Whereas E down here, what would we call that instead? Residual or leftover variance, right? It's the variance that's not due to x. And this same difference in terminology applies when you refer to any variable in the model. By itself, without brackets around it, you are either referring to its variance, if it is a predictor, if it's not being predicted by anything, or you are referring to its residual variance if it is being predicted by something. So variance if it's a predictor, residual variance if it's an outcome. So which are these? These are outcomes, or are they predictors? They're outcomes of the trait. So these are residual variances we're asking for. We're asking for the amount of not the factor in each of these. These are also estimated by default, and you don't technically have to write this line. So these 3 lines then give us our 3 types of measurement model parameters, our 3 item things. First line is loading, which is our slope. Second line is intercept. Third line is error variance. Error variance / residual variance / unique variance / specific variance. Take your pick. I'm going to stick with not the factor. I wonder if YouTube will get mad at me for playing the dinosaurs video from YouTube in my YouTube video. I'm going to have to find that. We'll get that one out next time. That may take a little bit of digging. So each item then has 3 parameters. That's our measurement model. Our structural model then is factor things. Because this is only one factor, I have one variance and one mean. So sit at 1. If I refer to any variable in the model by itself, I'm talking about a variance or a residual variance. The at means, no, make it this, fix it, don't estimate it. I want it to be 1. Is that a variance or a residual variance? It's a variance because it's the predictor. Once we get into SEM territory, where our latent variables themselves are being predicted by other things, this would be referring to its residual variance instead, which would be problematic because you want that to be estimable. You want it to be able to change based on what's predicting it. But right now, because it's just a predictor, nothing's predicting it, it's at 1. It's nailed down to set the scale of our latent variable, variance of 1. Likewise, sit at 0 inside brackets refers to the mean of the latent factor as 0. So we have identified our model. We have set the scale of the model such that the factor is distributed with a mean 0 and standard deviation of 1. And that means we can estimate all the loadings, all the intercepts, and all the error variances for each item. Okay. Questions? All right. So here's some output. So factor loading shows up first, followed by factor means, followed by intercepts. The 4 columns. Now this has changed across versions of M+, and it also changes when you ask for ML solutions versus Bayes. But in almost everything I think that we're going to look at, the estimate is the answer. So this is my unstandardized solution. So these are factor loadings here. Note that this right here is not given to you. This is me being nice. This is what you get. Sit by. You're supposed to remember that that means factor loading. And this is why I have a job. Likewise, they have a label means, and I added here of factor. They had a label intercepts, I added of the items. Variances, I added of the factor, and then residual variance is their label. So the estimate is the first column. The standard error of that estimate, the index of how precise it is, where that number is going to be smaller when you have more people. That estimate divided by an SE is computed for you in the third column. Some of you should know what this is called. If you've had me before. Or even if you haven't, you might know what this is called. It's a special name, estimate over standard error. The significance of fixed effects was assessed using, close. Closer, looking for the generic term. Starts with a W. Wald test, yes. This is called a Wald test. And Tyler, you said T, but you were very close. Pick another letter. Wrong way. Z, yeah. Do you see a degrees of freedom column? Nope, that's the difference. So T is when you test one thing with some kind of denominator degrees of freedom based on your sample size. Z is when you test one thing assuming infinite denominator degrees of freedom, and that's what this is. So these are Z tests. T squared is F, and Z squared is chi-square for the multivariate versions of each. But these are univariate Z tests, and this means that for 1 degree of freedom, a Z score of 17 has a p-value that is 0 to the 3rd decimal place. For 1 degree of freedom, meaning one thing tested. This one loading is what we're testing here. It has an estimate of 1.2. 1.2 divided by 0.07 is a Z-score of 17. And how likely is a Z-score of 17 on a normal distribution, folks? Not very likely. So yes, this is a very significant factor loading. So in contrast to what you're typically used to looking at for like predictors and regression or multi-level or something like that, these are always going to be significant. That is not a thing. If your loading isn't significant, then that's like really, really bad. That's a pretty low bar to cross in here. Because that's the point. Like that's the only thing that that item is there to do is to measure this factor. And if it doesn't have any relationship at all, then it's a terrible item. It's terrible. Sorry, I'm adopting my Marcy voice. My mom sounds like Marge Simpson, usually. That was terrible, Lisa. I can't believe that. Terrible. Now, I look at these numbers here, and these are the loadings of each of the items. You might be tempted to compare them and be like, well, 1 is better than 2, but we can't quite do that because these are unstandardized. Ish and no. They're all on a 7-point scale, but the scale, more specifically, is defined as how much variance is in each of these items. And item 1 has a variance of 3.0, whereas item 2 has a variance of 1.9. So the unstandardized loadings are going to be different simply because of that, regardless of how related those items are to the trait. That's why we need the standardized solution to figure out which items are relatively better than each other after correcting for differences in their variance or their scale.
Sort of in practice, that means that if there are particular items that cluster more in a different part of the scale than the other part of the scale, that accounts for this?
Not exactly. The scale is one thing.
On the response item. So like if responses cluster in the 5 to 7 as opposed to in the 3 to 5.
Yes, if there's there's a limited variability in response.
For some items, but not others.
Then that can cause a different loading for that reason alone.
Okay.
Yeah. Yep. The bigger the variance, the smaller the loading. As I get that correctly. I usually get it backwards, but I think that's right. You're going to see in some of your output this 999. That is not a Z-value of 999. That is a, hey, you asked me to fix this, remember? And so it doesn't know what to say, so it just picked 999. So we fixed the mean of our situation factor to 0. That's why it doesn't have a standard error and it doesn't have a test for it, because that is a fixed, nailed-down thing. Other item things of interest here, here's our intercepts. Because we set up the model so that our factor mean is 0, these are the means of the variables. And that's why the term item mean versus item intercept is frequently misunderstood, is because in this one method of identification, the intercept is the mean. But it's not guaranteed to be in other methods. It's only when the factor mean is 0 for identification that that's true. So these are the expected item response for someone with an average level of my trait. The variance of my trait is 1 because that's what I said it was going to be. So it's another fixed parameter. And these are my variance due to not the factor. 1.5 for this, 1.4 for that, and so on. So there is significant variance left over in each of these. That's, again, not surprising. So here's then what the model says in terms of getting back to the original data. You can predict for any person what their responses would be to these items based on an anticipated factor score. There's the formula. So for Y1, we take its intercept, which was estimated at 4.547, plus the loading, 1.234, times whatever value of the factor. And then we don't fill in anything for error because this is an expected value, and we don't know what error would be for an average person. It averages out to 0. So this will be one of your homework questions, by the way, asking you to do something like this. I don't make you fill in matrices, but I do make you do basic addition. Does that seem fair? I think at this point that should be a reasonable thing to ask. I don't make you do it in your head or on scratch paper. You can use Excel or calculator, whatever. Now, writing out the model. How well did this model do? Remember, the goal is to explain, to reproduce all of the covariances among these 6 items. If we go back to our picture, the covariance between, let's say, number 1 and 2, the predicted covariance by this model is the loading for 1 times the variance of the factor times the loading for the other. There it is. So this model says that item 1 and 2 should have had a covariance of 0.866. In the data, the covariance was actually lower. It was only 0.577. So we're off. How bad that is going to be contributing to our measure of fit, because we'll have each of these offnesses for every possible covariance. And I did the math for you. There's an Excel sheet that goes with this example, because I'm the kind of person who it helps them to see the numbers worked out for things, and so I tried to do that. So for instance, here is my original covariance matrix for the 6 items. That's the answer key. That's what we're trying to get back to. Here is what the model says that it's going to be. So there's my 0.577 from the data. There's the 0.868 that we just figured out. And here are the rest of them. I literally took the difference between the data matrix right here and the predicted matrix right here, and I'm calling it residual or difference, left over. So here's the pattern of misfit. Now, do you notice something curious about this that Excel is very concerned about with its dashes? What's on the diagonal? The item's variance. And how well did I do?
Really good.
Nailed it! Am I just that good, or is there a reason for it?
Because it's perfect when we have mean.
Yeah, she's heading in the right direction. Someone help her out. Why am I perfect on this diagonal?
Because you have the intercept of it, or the mean of every item.
No. Nope, that ain't it. Heading in the right direction, though. Here, I'll put this up here to help. Why are my variances perfect? Because I what? Nope. That's how I was able to estimate my model, is by giving the latent variable a scale. But remember, that's just like picking a key in Happy Birthday. Yes. Nope, not item means. Got to drop the means for a minute. We're on variances. Other side of the model. These. Each item gets its own residual variance. So what does the model say the variance should be? Let's go to that. Right here. The variance of item 1 is supposed to be whatever the variance of the factor is, which is 1 in this case, times the loading for item 1 squared. So that works out to be this much. What is 1.2 squared? 1.34, let me figure that out here, equals 1.234 to the power of 2, 1.5 something. Well, the model did this much. There's 1.5 something. I know that the right answer is 3. What's the difference between 3 and 1.5 something? 1.5 something. Ta-da! It fills in the gap. Whatever the gap is, it's just going to fill it in. So every item is part factor and part not the factor, right? The part factor is what the model is focusing on. It estimates loadings that create that much of it. But we know in the data what the true variance has to be. So we have two knowns and one unknown. We only need 2 out of 3 to figure out what the third thing is. So to the extent that each item gets its own residual variance like it does here, the variances are always going to be perfect. And that's what this note says, by the way. Variances are perfectly reproduced. And the fact that I'm off is because of rounding error. I only took 3 significant digits. The rest of these are covariances, and they are off to some degree. And that's because there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 covariances. And what did we use to try and capture them? Starts with an L. 6 loadings, yep. So to the extent that 6 is not good enough to represent 15, you're off. That's the basis of model fit, which is coming next. So Emily, to the point you were saying, these are the item means. They're perfect because each item got its own intercept. So whatever offness in prediction you would have, the intercept can stretch to accommodate it.
So the model isn't making a guess about the variance of the given item, and it's not making a guess about the mean of a given item.
That's data in. It knows.
Okay.
Yep. Once it has figured out what the loading is and the factor variance, it knows this, and it knows this. It just has to figure out that. Once you know 2 out of 3, you get the third. It's like when you represent a 3-group variable in a model with 2 dummy codes. You don't need the third. It's a linear combination of what's already there. Okay, how are we doing? So take home so far. No one cares about means. No one cares about variances. The show is about covariance. So long as each item gets their own intercept, the means are perfect. So long as each item gets its own residual variance, it plugs the hole to become whatever the total variance would have already been, and it's perfect. To the extent that you have fewer loadings than possible covariances, that's where the show is. That's where you have the potential to be wrong, and that's where it becomes testable. So let's look at the loadings. These are unstandardized loadings, and as I said before, you can't really compare them because it depends on how much variance each of these items had to begin with. But if we flip on over to the next page, we hit the STDYX standardized solution, which re-standardizes those into a total variance for the item of 1 and a factor variance of 1. So these sit by things. Note the column headings are the same. It's up to you to infer that all of these are standardized based on the label at the top, STDYX. So these are the standardized loadings. They are directly comparable with each other, and they have a very ready interpretation as the correlation between that item response and the factor that it measures. Bigger is better. What's the best standardized loading that you could have? 1. What's the worst that you could have? 0. -1 or 0? I'd say 0. If you get -1, double check your coding. If you still get -1, go ruh-roh, because it's working backwards. It's predictive, just in the completely wrong way. 0 means no relationship. So now we can look at the relative size of these things. Which is my best item? Which number is highest? How do we put it this way? 3, yeah. What's my second best item? 1. What do items 3 and 1 have in common? They're reverse coded. What's my next best item? 5. What does that have in common? It's reverse coded. So these are clues, right? Before I even look at fit, these are clues. The fact that the R items have higher loadings, meaning whatever this factor is, whatever I'm calling it situation, but right now it's just, it's a pile of covariance with a name. It's more of whatever R is, meaning it's not forgiveness. In this case, reverse coded, so it's not unforgiveness. That's what I would call it. The positively worded items are measuring forgiveness. A reverse coded negative item is measuring not unforgiveness. So this is the not unforgiveness scale. All of these, mind you, are significant. These are your effect sizes from this type of analysis. So if this is R, a correlation between the item and the factor, R squared is down here. So your standardized loadings squared get shown up again as an R square, which is how much of the indicator of the item's variance the factor has accounted for. There are no hard and fast rules about what is good and bad, but anything under like 0.3 makes me squishy. I'll just tell you that. That's a personal thing. I figure it should be at least 30%. So no matter what happens in terms of your type of identification, let me go back to the original model here. So we decided to fix our variance to 1 and fix our factor mean to 0. If I had decided to make this 100 and 0, the standardized solution would be exactly the same. The standardized solution is impervious to methods of identification. It will always be the same. Yes. The standardized solution, right here, this page, will always be the same no matter how you've identified your model. It's impervious to differences in scale. And that makes it useful for looking at the relative differences across your items. It makes every item's total variance 1, and it makes every factor's variance 1. So the best possible item you could have would have a standardized loading of 1, meaning it has a perfect correlation with the factor, and that would translate into an R square of 1 as well. Question?
Have factors that are really, really highly, or items that are really, really highly correlated with your factors. Do you need all of them?
Maybe. What we haven't talked about yet is reliability, which is how well the factors are being measured, and that depends on the number of items and the strength of their loadings. Other questions? Okay. So here then, in using the standardized model estimates, the job of the previous solution, unstandardized, was to recreate the model variances and covariances. The job of the standardized solution is to recreate the correlations. So we can do the same thing. The correlation between y1 and y2 is the standardized loading for y1 times the factor variance that's been standardized to 1 times the loading for y2. That works out to be 0.36. That's what the model says these items should have as a correlation. In the real data, though, it's actually only 0.24. So the model thinks these are more related than what they actually are. Misfit. Evidence against unidimensionality. Let me show you what the results look like if you choose a different method of identification, if you use the M+ default. And I promise I won't sing at you this time unless you want me to, but this is the idea of picking a different key for happy birthday, right? It's still happy birthday, just starting in a different place for what 1 means. Here's the same code, sit 1 at 1. So I have changed the method of scaling for my factor variance to borrow its variance as the reliable part of item 1. So item 1 is not going to have an estimated unstandardized loading. I've nailed it down to 1. Instead, the situation factor is going to have an estimated variance. It's one or the other. One of them gets fixed to 1 and one of them gets estimated. And why did I make it item 1? Because that's what M+ does. Would the model fit better, do you think, if I made it item 6? What do you think? Yeah. What do you guys think? No? A lot of people not answering. If I made the marker item 6, would that make it better? Nope, that's just another key. Another possible key. Doesn't matter what the marker is, so long as it's related. I'm keeping the other side of the model the same, meaning the mean side. Factor mean is still 0. All of the intercepts are being estimated. That's what M+ does by default. So now here's my new factor loadings. Note that the first one is 1, just like I said it should be. And everything else has rearranged itself around that. So 2 is still much smaller than 1. Proportionally, it's the same. The factor variance has been estimated as 1.523. We saw that number just a minute ago. That's what, from the previous model, the unstandardized loading squared gave us. It's the part of the variance of item 1 that's due to the factor. It becomes the factor's variance when you fix its loading to 1. Now, why people do it this way, why it's the default, is because then in this model, you can have that factor be predicted. It can be an outcome, because that 1.5 then can go down as you add predictions of it. Why I don't set it up this way when I'm first fitting measurement models is because I don't want to have to keep track of what the standard deviation is to interpret things. I want it to stay constant so that I can make plots and think about what my factor scores mean in a sort of a constant context. So that's a choice. There's not one that's right and one that's wrong. It's just my own preference in how I set things up. But this is the software default, I think, in most cases, is to estimate the factor's variance and fix one of the loadings to 1, usually the first thing you write. The intercepts are still the means because the factor mean is still 0. The residual variances are still the same because it's still the same amount of variance that's due to not the factor. And then last but not least, here's another combination where I keep that method for estimating the factor variance instead of the first loading. I fix one of the intercepts to 0 instead of the factor mean, and I estimate that. And here in this case, the intercepts rearrange themselves such that the factor mean then becomes the mean of item 1, and everything else is relative to that. Just a different key, same song. And all three of those methods of identification would lead to the same standardized solution on the previous page, which is why I did not print it out again. There. How are we doing? I want to fast forward to something just to show you a picture real quick in the few minutes that we have left. So we talked about normality, right? And continuous data, that's what this is for. And I showed you how to take an unstandardized solution. Hang on, come back. And create a predicted outcome for it, like this for Y1 right here. Well, if this factor score has a standard deviation of 1, I can plot out what expected item responses would be at reasonable levels of my factor. And that can give me some indication as to whether a linear model, a CFA model, is going to be appropriate. So this is the tab that I added more to and asked you to re-download on Monday. But here's the result for what's going to become the positive factors. So we're going to end up splitting the R's from the other ones into a two-factor model. And the two-factor model is going to give us a picture that looks like this. So I literally just plugged in these values for F as plausible factor scores, ranging about plus or minus 3 standard deviations. I used the estimated intercept and loading from that model, and I made this picture. And on the picture, I also included lines for the scales minimum and the scales maximum. So what do you think? Is a linear model plausible for these 3 items? Up to a point, right? Up to a little bit before a theta of 2, they have something to answer. Somewhere around here, here are the negative factor items and their intercept and loading predicted lines. Now what do we think? 2-ish. So there's no hard and fast rules about this, but these are the kinds of pictures that can supplement your analyses to indicate, well, do I really need some kind of nonlinear model? If your predicted outcomes go out of bounds for expected values of your trait, then probably, yeah, some kind of linear model would be better. And the article that I added to your reading list for today, the Fernando one from 2009, I inputted his formulas from that article into the spreadsheet, and it allows you to calculate the precise value of the trait at which your responses go out of bounds. So for these 3 items, for instance, this last item is pretty good. They don't run out of responses until minus 3.8 standard deviations or 2 standard deviations. For this one here, it hits the upper end at 1.5. So I think this kind of information can help to convey, to answer your question, besides just the model, then whether or not this is actually a plausible model from a prediction standpoint. So I'll leave you with that. So, questions? Okie dokie. Then I think that's all. Office hours start now if anybody wants to hang out and chat. Otherwise, I will see you next week.